Hello, everybody. Welcome to our keynote speaker this evening. I'm delighted to welcome John Campbell. He's written well over 100 influential papers in finance, econometrics, and macro, and books as well, many of them, of which is my favorite financial econometrics textbook. Even 25 years on, is still my favorite, The Econometrics of Financial Markets. And John has co-edited the American Economic Review and the Review of Economics and Statistics. And we're delighted to have him talk about sustainability in a risky world today, a world that became even riskier than a week ago. Thank you, John.
Thank you very much, Karim, for that kind introduction. I'm really glad to participate in this conference. And as you say, the world is very obviously risky. This is also a world in which many people are concerned about sustainability. And so my co-author and I are trying to bring those two topics together. So my co-author is Ian Martin from LSE, a former student of mine, but one of those former students who's taught me more than I ever taught him. So the question we're going to talk about is whether it's ethical for society to act in an impatient way. And just to be clear, the focus here is really on how much society can consume. So impatience leads to consumption. If you consume not very much, then you're saving for the future. The future will look good. If you're very impatient and you consume a lot, you will be running down society's resources and the future will look worse. So we're thinking about impatience and how it feeds into the amount that society consumes. We raise the question of whether impatience can be ethical. And there's really three views of that. One is the traditional economist's view that preferences are what preferences are. We don't argue about them. If people are impatient, they have a high rate of time preference, and they choose to run down consumption over time so that the future looks impoverished relative to the present, well, that's just what preferences are. We have to take them as given. The second view is that at least when one is thinking across generations, so thinking about a social rate of time preference, that it's unethical to have a positive rate of time preference because that is privileging current generations over future generations. Famously, Frank Ramsey expressed this view in his 1928 paper that really founded growth theory. More recently, this view was an important influence on the famous Stern report on climate change in 2006. The Stern report used a low discount rate and cited this view that the pure rate of time preference should be 0. The final approach is that what ethics does is to impose a sustainability constraint on time preference. So we can't let time preference get so high that we behave unsustainably. And this is the perspective that we're going to adopt in this paper, and we're going to just follow the idea and see where it leads. All right, so what is sustainability? Famous definition given by in the 1980s by the so-called Brundtland Commission on Environment and Development. They said a sustainable consumption plan, quote, meets the needs of the present without compromising the ability of future generations to meet their own needs. And leading economists have endorsed this. So Bob Solow, for example, in '93, argued that the duty imposed by sustainability is to bequeath to posterity not any particular thing, but whatever it takes to achieve a standard of living at least as good as our own and to look after their next generation similarly. So we're going to take that, and I'll talk about how we formalize that. We're going to take that as a constraint rather than building it into the objective function. And this is pretty unfamiliar approach to many economists who tend to be utilitarians. We tend to want to write down a social welfare function and maximize it. Instead, we're going to be operating with a constraint given by ethics. That actually is consistent with the positions of many moral philosophers, including most famously John Rawls in his theory of justice. He argued that ethical considerations, which he called principles of right or justice, impose restrictions, or if you like, constraints, to use economists' language. All right, now, how do we formalize that? It's pretty straightforward in a riskless world. A few years ago, Ken Arrow and a large number of co-authors wrote a paper in Journal of Economic Perspectives laying this out. And they said, let's think about a single form of capital which has a constant riskless rate of return. So there's some sort of productive technology, it's riskless, you can save in it. In terms of growth theory, it's an AK model with no risk. Well, the sustainability constraint then says that the social rate of time preference cannot exceed the riskless interest rate. When the constraint binds, time preference is equal to the riskless rate. And then what happens? Well, society consumes the return on capital, the riskless rate, and leaves the capital itself, the principal, unchanged over time. So then consumption, wealth, the utility of consumption, the marginal utility of consumption, and social value, by which I mean the discounted present value of utility, all of those things are constant over time. The world is completely static, nothing ever changes. So of course it's obviously sustainable. Now, to make a rather obvious point, this approach only makes sense, it only works when the riskless rate is positive. And then positive time preference is sustainable. So the sustainability constraint is not as tight as Ramsey's imposition of a zero rate of time preference. In other words, if there's a positive risk-free rate and you do Ramsey, then consumption grows over time, because with a zero rate of time preference and a positive riskless rate, you accumulate capital over time. So sustainability then, the implications of sustainability are related to what technology allows. And this relates to an old debate back in the 60s where Charling Koopmans famously criticized Ramsey by saying that the Ramsey criterion ignores technological possibilities and can sometimes produce nonsensical results. I mean, an obvious example of a nonsensical result would be if you think people have log utility, then the amount you choose to consume is the rate of time preference. The consumption wealth ratio is the rate of time preference. If that's zero, then you consume zero. So nobody ever consumes anything. So that's obviously absurd. All right, now the thing we're going to do in this paper is think about risk. In a risky economy, the return on capital is uncertain. So it's actually infeasible to guarantee that social value remains constant over time. We might want to protect our children and grandchildren so that they're as well off as we are. But if there's randomness, we can't guarantee that. Bad things could randomly happen, and then they'll be worse off than us. So what we do is we impose a weaker constraint, which has been suggested in the literature but never formally analyzed, that social value is not expected to decline over time. It can be driven down by random shocks that are bad shocks, or up by random positive shocks, but in expectation, it's constant. Now, this is related to some other work I've done recently. I have a paper with Roman Sigaloff that just came out in the JFE in January. And we looked at constraints on sustainable spending with an eye to endowments and sovereign wealth funds that are allowed to spend the expected return on their funds, but they're not allowed to spend more than that. And so they're not allowed to plan for declining consumption or possibly log consumption over time. So this idea of restricting the drift in something is common with my earlier work. The difference here is that the earlier paper with Sigaloff restricted the drift of consumption, and here we're restricting the drift of utility, and that turns out to make a difference to what happens. So, you know, the outline, and I'm not going to go into all the details in the interest of time, but let me just set up a model, sort of a familiar model, at least to finance people. So it's consumption and portfolio choice with a riskless and a risky asset. It's the classic Bob Merton model of an infinitely lived investor. We're going to assume IID returns, so it's a very simple world. We think for this problem of sustainability, which is really a long-run problem, we can ignore the short-run fluctuations in risk and return that are important in the short run, but less so on a scale of generations. Then we're going to impose the sustainability constraint on this problem, and we'll compare the constrained and unconstrained solutions. I'll show you what the drifts look like for wealth and marginal utility when you impose the constraint. Remember, the constraint says utility can't drift, but it turns out that both wealth and marginal utility drift upwards, which may seem counterintuitive, but we'll explain why that is. I'll show you some numerical examples. Then I want to talk about what happens if there isn't a riskless asset. So there's only one risky technology. That's the case where society can't escape risk. And then I want to talk briefly about what happens with population growth and then conclude. Okay, so moving ahead, I'm going to show you a model. All right, what are the ingredients of the model? This is just the Merton model. Society, when think of a representative investor, society has two assets. There's a riskless rate, safe return RF, log return RF. Then there's a risky asset, and it has a risk premium of mu. That's the equity premium. It's got some Brownian volatility, the standard, normally distributed risk with standard deviation sigma. But we're going to allow for jumps as well. So by allowing jumps, it's a Poisson process with a constant arrival rate. So it is not the absolutely most general IID continuous time process, which would be a Levy process, but it's pretty general. And it still allows us to get nice analytical solutions to things. Now, given that there are jumps, if it's helpful to define the equity premium if no jumps occur, and that we call mu hat. And mu hat is just mu plus the jump arrival rate times the expected jump size. So you're just correcting for the jump. We define this L as a negative jump. So when L is positive, then you're jumping down. Then there's a representative investor who's choosing the consumption wealth ratio. We call that theta. It's constant over time in this IID model. So you choose theta, and you also choose your risky portfolio share alpha to maximize discounted power utility of consumption with risk aversion gamma. And the budget constraint says that consumption growth, which is the same as wealth growth, is the expected return on the portfolio plus the unexpected return, which has two pieces. There's the Brownian piece dz and the jump Poisson part dn. Okay, so just the Merton model with jumps. Now, where does this come from? What are the microfoundations? In the paper, we're taking the representative investor's objective function as given, but a plausible microfoundation would be the one offered by Olivier Blanchard in his perpetual youth model in 1985. So in that model, you have individuals who have a constant probability of death, so they have finite life expectancy. There's no population growth, so each deceased agent is replaced by a newborn, and the wealth of the deceased agents is given to the newborns. In that model, all the agents alive at a given time are identical, and the time preference rate in the objective function reflects a mix of the true rate of time preference within each individual's lifetime, the death probability, the mortality rate, which raises the time discount rate, and any degree of intergenerational altruism caring about future newborns, which would lower the time preference rate. So then if that's the microfoundation, what the sustainability constraint does is it protects the interests of future generations, the future newborns, versus those people who are currently alive. The framework can accommodate population growth, but I'm going to defer that to the end. Okay, so we have this Merton model. What's the unconstrained solution? Well, you can rewrite the objective function in terms of the parameters of the model, and there's sort of messy looking expression involving theta and alpha and the various other parameters. But you basically can maximize this thing with respect to alpha and theta. You get this solution on the slide for the unconstrained optimal consumption wealth ratio. And unsurprisingly, if rho is high, if people are impatient, then they consume a lot. Okay, and we'll show actually that if rho is high enough that it is higher than this unconstrained consumption wealth ratio that you see on the slide, then that's an unsustainable situation where expected utility is expected to decline without limits. So the future generations are going to be worse off than the present. We can also solve for the optimal risky portfolio share in this model. Find the optimal alpha. It's defined implicitly by this second equation on the slide. If there are no jumps, you get the classic Merton formula, which is in every textbook, including mine, that the risky share is the risk premium divided by risk aversion times variance. So that's what falls out if the jump L is 0, but the general formula is above. Okay, now what we do is impose a sustainability constraint. So this is where we do something new. We're going to impose a 0 drift in expected utility, or equivalently a 0 drift in xt, which is just wealth to the power 1 minus gamma. What's the stochastic process for x? It's written there on the slide. And we want to make the drift in that thing equal to 0. So in other words, the first term and then the expectation of the third term, the jump piece, that all has to add up to 0. So if the constraint binds, in other words, if the drift literally equals 0, then we get this expression down here for constrained consumption wealth ratio. And if we use that, we can eliminate theta from the objective function, maximize with respect to alpha to find the risky portfolio share, and we get the same solution as before. The sustainability constraint does not distort portfolio choice. Now that's actually a contrast with my earlier work with Sigalov, where we showed that if you constrain spending to have a 0 drift, then it does distort portfolio choice. And actually you get reaching for yield, meaning that as the risk-free rate goes down, you take more risk. That's another paper. That's a different result. Okay, so in this context, nothing interesting is happening in portfolio choice, but what's happening to consumption? Well, we use the solution for alpha to rewrite the constrained consumption wealth ratio like this. You notice that you've got the risk-free rate, and then you've got a variance term, a Brownian variance term, and then you've got a term involving the jumps. When the risk you take and the risky portfolio share are both positive, then both of these second two terms are positive, and that tells you that the sustainable consumption wealth ratio exceeds the riskless rate. So this is different from the world analyzed by Arrow and his co-authors, where you couldn't be any more impatient than the risk-free rate. You could never consume more than the risk-free rate. In a world with risk and an equity premium, it's optimal to take some risk, actually take the same risk that you would if you were unconstrained, and then consume more than the riskless rate. And you can do that because society is earning a higher expected return than the risk-free rate. So obviously risk is critical for this result. Now, the constraint is an inequality. It's one-sided. If people are so patient that they privately allow expected utility to drift up rather than down, we're okay with that. If people want to make children and grandchildren very well off, we're not going to prevent that. So what that says is that we allow the consumption wealth ratio to be lower than the constrained level. So the sustainable theta is the minimum, the lower of the unconstrained and the constrained. Then if we compare the two, compare the constrained and unconstrained, we can write the unconstrained consumption wealth ratio as a weighted average or combination, linear combination of rho, the unconstrained rate of time preference, and the constrained theta that we were just talking about. And the weights are 1 over gamma and 1 minus 1 over gamma. So that shows you that the constraint binds if and only if rho is greater than the constrained theta, or equivalently greater than the unconstrained theta. We also see that the constraint has a smaller effect on consumption when gamma is very large. Why? Because then if you're very risk averse, you want unconstrained a very flat consumption path. So no matter how impatient you are, you want a flat consumption path. You stay very close to sustainability, even without the constraint. Finally, what this says is that if you're a social planner and you want to implement the constraint, you can do it by imposing an adjusted time preference rate, rho hat, which is the lower, the minimum of the unconstrained rho and this constrained solution for the consumption wealth ratio that we've been talking about. Okay. Now, we've set up a model in which utility has zero drift when the constraint binds. But in that model, wealth actually has a positive drift. And the positive drift in wealth means that this sustainable utility constraint is actually tighter than the sustainable spending constraint that Sigaloff and I imposed. The intuition here is that in a Merton model, risk accumulates over time because the shocks come in, there's more and more uncertainty. Think about one of those fan charts where you know where you are today, but over time the uncertainty accumulates, the fan widens out. So later generations are exposed to a lot more risk than we are. And to compensate them, they must have higher wealth in expectation. We need to allow them to be richer on average to compensate them for the risk that they're exposed to. Now, it's also true, actually, that marginal utility has a positive drift. So I'm going to write M for marginal utility. That's W to the minus gamma. That drifts upwards. That's actually another way to understand the result that the constrained theta is bigger than the risk-free rate, because the first order condition for optimal investment in a riskless asset implies that the expected drift in marginal utility is the difference between those two things, the difference between constrained theta and the risk-free rate. So since theta con is above RF, that means that the drift in marginal utility is positive. Now, you might be scratching your head at this moment because X, which is the thing that is the transformation of utility that we're working with, that has a zero drift. And it's the product of M and W. So how can the left-hand side have zero drift when both the things on the right-hand side have positive drifts? Well, the answer is that the two things covary negatively. And the drift in X is the sum of the drifts in M and W and the quadratic term, the cross product term. Because that quadratic term is negative, it resolves the paradox. So once again, risk is critical. Okay, now, what happens if we turn off these messy looking jumps? Suppose it's just Brownian risk. Then we can plug in the Merton portfolio rule, alpha is mu over gamma sigma squared, and we get a super simple answer. We get that the sustainable consumption wealth ratio, or sustainable rate of time preference, is the risk-free rate plus the risky share times half the equity premium. Or equivalently, it's the average of the riskless rate and the return on the optimally invested portfolio. So you're holding a portfolio that gives you more on average than the risk-free rate, but you can't consume the whole expected return on that. You have to save some of that to give to the future to compensate them for the risk. It turns out that you have to save half of the extra return that you get from your risky investing. You eat half of it and you give half of it to the future. So, here are numerical examples for Brownian motion. So, suppose the risk-free rate is 1%, the equity premium is 8%, the vol of the market is 20%. That means the Sharpe ratio is 0.4. We can consider different coefficients of risk aversion, 1, 2, 5, 10. Here's the sustainable consumption wealth ratio. As you see, it's always much above 1%. A benchmark case might set risk aversion of 2, then you can consume 5% of your wealth. If your risk aversion is 5, you consume about 2.5% of your wealth. The last 3 columns show the drift in wealth itself, that's positive. The drift in log wealth, also positive whenever you have risk aversion above 1, and the drift in marginal utility. So both wealth and marginal utility are drifting up, total utility is not drifting. We can extend this to think about jumps. So we've got a whole bunch of numerical examples. Here, risk-free rate is 2%. We've got less Brownian risk. There's still a Sharpe ratio for the Brownian piece of 0.4. So we've got sigma of 10%, mu is 4%. But then in addition, there's a 4% arrival rate or probability per year of a 40% crash. So there's this negative tail risk. Baseline model, risk aversion of 2. We find that the constrained consumption wealth ratio is 4.5%. And then the rest of the table is ringing the changes, either increasing or lowering risk aversion, or the risk-free rate, the equity premium, the Brownian risk, the jump arrival rate, the jump size. And you can see that, there are intuitive effects on this sustainable consumption, but it's always considerably above the risk-free rate of 2%. And that's the key message of the paper. Now, we can ask, well, what would equilibrium look like in the case where there isn't a riskless asset, where there's just a risky technology that society faces, kind of like a Lucas tree model, except that you can you've got a technology, you can scale up capital. So it's an AK growth model, but with risky technology. Well, then, of course, we're used to this in finance. We impose alpha equals 1 in equilibrium because the riskless asset is in 0 net supply. And the risk-free rate adjusts to be whatever it needs to be to make investors content to have alpha equals 1. The Brownian solution then becomes the sustainable consumption is the risk-free rate plus half the equity premium. It's the average of the riskless interest rate and the risky return. Same intuition as before. Now with jumps, it's a little bit more complicated. We get bounds. We don't have a closed form solution, but we find that the sustainable consumption wealth ratio lies between these bounds, a lower bound of risk-free rate plus 1/2 gamma sigma squared, and an upper bound of risky return, RF plus mu, minus 1/2 gamma sigma squared. And depending on whether jumps are bad or good news, the upper or lower bound can be approximately tight. So I'm just going to illustrate this for you here in a particular parameterized model where the only thing that's varying on the horizontal axis is the jump size L. Remember, L is for loss. So 0.2 means that with a certain probability, you jump down by 20%, you lose 20% of your wealth. 0.4 is a 40% crash, 0.6 is a 60% crash. The negative numbers on the left are negative crashes, or in other words, upward jumps in consumption. Benevolent aliens arrive and give us technology and consumption jumps up. And the 0 point here in the middle is the Brownian case. So the green line shows the equilibrium risk-free rate, which of course it falls as jump risk increases to the right. The blue line is the risky return, which we've assumed to be fixed in all these cases. And oops, sorry, I have to go back here. The yellow line is the sustainable consumption wealth ratio, which in the Brownian case is exactly at the midpoint. And then you can see that as we move to the right, the gap between the yellow and the green gets bigger than the gap between the yellow and the blue. Okay, now the bounds, this is now showing the bounds. So instead of RF, I show RF plus gamma sigma squared over 2. And instead of mu plus RF, I show that minus gamma sigma squared over 2. And we know that the yellow line always must lie between the blue and the green lines. The bounds are completely tight, of course, in the Brownian case. Again, we can look at numerical examples, but again, the message is that however we play around with this, we're always going to get a sustainable consumption wealth ratio that is very considerably higher than the risk-free rate. How much higher depends on some of the details of the model. We're also going to get upward drift in wealth and upward drift in marginal utility. Now, I'm almost done and almost out of time. Let me just mention how population growth might feed into this. So our first point is that population growth is notoriously challenging for intertemporal ethics, particularly when population is endogenous. So if population is being chosen by people today through their decision how many children to have, then how do you value a given person in the future? It's very tricky. So moral philosophers like Derek Parfit and economists like Partha Dasgupta have written books about this. We're just going to make one very simple point in this paper. We can accommodate exogenous deterministic population growth if we assume that it's the utility of a representative newborn individual that must have zero drift. Well, in that case, you know, since with population growth, the wealth of the people who die has to be shared among a growing number of people, growing number of newborns. We need to, and there's always more newborns than people who just died. We need to increase saving to compensate. And it turns out that the sustainable consumption wealth ratio declines by the population growth rate G. So whatever numbers I just showed you or plotted in a figure, you just subtract G, where G is the population growth rate. Now, then of course, the sustainable consumption wealth ratio can be lower than the risk-free rate. But for realistic parameters of the kind that we've been looking at, it will actually remain higher than the risk-free rate as the various tables and figures show. And of course, the opposite is true. If the population growth rate is negative, as is true in more and more of the world today, then it'll go the other way. The sustainable consumption wealth ratio will increase further. All right, so, you know, conclusion, what have we done here? The point we're making is that in a risky world, the ethical criterion of sustainability doesn't require us to have an extremely low rate of time preference. Society can have quite a substantial rate of time preference and consume quite a lot out of its wealth. And of course, for a social planning sort of problem, we should define wealth very broadly. We should include many things that are not included in the standard financial definition of wealth. And we should think about consumption very broadly. But when we do that, we can allow ourselves a substantial rate of time preference and a substantial consumption wealth ratio. And the reason is basically that high risky returns make it attractive for society to save for the future, even if people are impatient and would save if they could only get the low riskless interest rate. Now, importantly, everything I've been talking about has to do with the consumption wealth ratio And I haven't been talking about the discount rate for investments. That's because the discount rate you apply to investments in the model we've been using is just exogenous, right? If it's a riskless investment, you discount it at the riskless rate. If it has the same risk as the risky asset, you discount at the risky rate. And in general, you discount according to the beta of the investment with the risky asset. So the general point is that in a risky world, there's no unique discount rate for investments. And people like Christian Gollier have made this point very effectively, and it's absolutely right, that if investments to mitigate climate change have insurance value so that they pay off in bad states of the world where climate change is severe, then you should use a very low interest rate, because you might have a negative premium in the discount rate to reflect the insurance value. So we're not directly commenting on that. That's just basic finance. We're getting at a slightly different issue, which is, given the interest rates and discount rates, how much to save and how much to consume. We've done all this using a very deliberately simple model, IID model, continuous time, stripped down 2 assets. So we've ignored some things that have been discussed in the literature, for example, parameter uncertainty, which my late colleague Marty Weitzman famously explored, or time-varying expected returns and the resulting term structure of discount rates. Lots of finance people have worked on that. I have, Christian Gollier has, or think of the long-run risk of model of Bansal and Yaron. They're all about the term structure of discount rates. We've ignored that. We think there are important points to make, even in an IID context. We should start with that. So let me stop there and see if anybody has any questions or comments in the remaining time.
Thank you, John, for a very interesting talk. Any questions from the audience? Well, I can start with a question. So choosing to keep the expected utility constant is one possibility, but in a risky world, I would want to guard against the worst case scenario, or maximin, or some other criterion. Have you considered the robustness of your results to that?
Yes, so actually that's a very interesting question, and we're currently working to do a little bit more on the philosophical foundations of this. So I gave you a quote from Rawls, and one natural way to think about this is to adopt Rawls's device of the original position. So, famously he said, imagine that all generations before they're born are up somewhere in the clouds, their souls in the clouds, they haven't been born yet. And they don't know when they're going to be born, or into what circumstances they will be born. And they all get together and they have a discussion about what would be fair and right, and what would be optimal. And Rawls, in his theory of justice, argued that we can use that thought experiment to decide what is ethical. Now, if you imagine that the souls are facing a lottery which will determine their birth order. So the lottery will be run up there in the clouds, and some people will be born soon and some people will be born late. You might take the view that they max min over that lottery. All right, that they want to ensure that the worst birth date is as well off as possible. So that would be max min across generations, but accepting that the risk of the risky technology is inescapable. So the only thing that can be decided upon, as in the rules of the game we're playing here, is how much gets consumed. And these souls in the clouds don't do any time discounting. They treat, because it's atemporal, they haven't been born yet, there's no sense of time. They're just considering a lottery over birth order. If they max min, then they're going to want to make the expected utility of the worst off generation as high as possible. Now, if utility is drifting up, then the worst off generation is the first one. And you make it better off by consuming more early and flattening the utility path. If, on the other hand, utility is drifting down, then the worst off generation is way off in the infinite future, and you make them better off by saving more and flattening the consumption path. The solution, the max-min solution, is exactly the sustainability constraint that I have used in the paper. So that would be one sort of philosophical micro foundation. Now, interestingly, you could say, well, these souls that haven't been born yet and face a birth order lottery, perhaps they're not infinitely risk averse. Perhaps they don't max min. Perhaps instead, they just maximize average utility in the lottery. Again, without time discounting. If they did that, you would get Ramsey. So this device of the original position with a birth order lottery can give you max min, which is sustainability, or it can give you zero social rate of time preference, which is Ramsey. So that's something we're trying to write up now as we extend the paper. But thanks for asking. It's a very deep and important question.
Thank you, John. We have another question from Xiaofei Ma.
Yes, thank you, John. And actually, when I see the title of your presentation, I was very much interested because I think this is something very much related to the current situation. I think on the one hand, in the world, they are all doing some ecological transition in their economy. For example, I'm in France, and there is a very big structural change toward the green economy here. Mm-hmm. We can consider it as a form of sustainability development.
Yeah.
And on the other hand, we see there are a lot of risks in the current world. For example, there are risks of the COVID. There is a risk of war. Yeah. So from this aspect, I think your presentation is very much pertinent to the current situation. And would you please give some, talk to touch a little bit the current situation, which might give something like a relation between your work and the current situation of the world. Thank you.
Well, that's a huge challenge for a piece of work as abstract as this. I think maybe one way to respond is to return to something I mentioned in passing, which is because we've been using the tools of financial economics, it might seem that we're just talking about conventionally measured wealth, stock market and housing and so forth, and conventionally measured consumption from the national income accounts. I think that any serious consideration of the environmental situation of the world has to take account of the fact that there is natural capital or environmental capital, and that it's that a large part of what we're doing in the world today is running down that capital. And so when I say, oh, we can consume a lot, I don't necessarily mean we can consume a lot in the conventionally measured way. I think we are already consuming a lot because we're not properly measuring it, because we're not measuring the effects of environmental degradation properly. So in any application of this framework, I think it's vital to take a very broad view of what it is, what it is that we're talking about. But similarly, you mentioned COVID. COVID is a great example of how we cannot guarantee that future generations are as well off as we are. I mean, with any luck, COVID will be relatively short-lived negative shock. But one can imagine a virus that, might really lower the standard of living in a very long-lasting way. I mean, economic historians think that the plague, for example, had really it wasn't just the 14th century, it was still causing a lot of damage into the 18th century. And so, and it plausibly may have, lowered the standard of living for a long period of time. So I think, there are risky developments. There's stuff that can happen that we simply cannot protect our descendants against. Now we should try to find the insurance policies and the risk limiting measures. We should certainly do that. But we should also react to such risk by accumulating wealth for our descendants so that we compensate them in the form of wealth, so that even though they're exposed to more risk than we are, all the shocks that we'll realize in the future, we decide to compensate them by giving them more wealth on average. And
Thank you, John.
That's an important principle for us to all think about.
Thank you, John. We've reached the end of the session. Thank you all, and thank you for the questions. And we continue with the last session afterwards.